All right, so I'd like to say good afternoon to everyone again. So this week is going to be our fourth week, and then our fourth week is going to talk about the mechanical properties of the material, right? Every time we start the class, we need to talk about what are our objective that we're going to complete for our chapter 4. So um, if you look at basically the chapter's name, we're going to talk about the material. Okay, so there are many material in our world, but we focus just only for our CE field because we are now in the CE course. So can you tell me the material that we're going to use in CE, like most used material? Can be how many materials? Say it loud. I cannot hear. We have steel, right? We have steel. We have concrete. Anything else? Timber, or we just basically call it as a wood. What else that you're going to test at the labs? We have cast iron, CI. Okay. What else? We have brick. Okay. So these are, I think, the most used material in our CE. So if we talk about the steel only, because we mainly focus on the steel. For example, if I pick up steel over here, so we have like many type of the steel. For example, we have like the structural steel. Structural steel. We have like reinforcement steel that we're going to use most of the time. Okay, reinforcement steel. So what are the difference between these two? So the structural steel is the one that you may have seen if you ever been to C1, the one that they are like doing the construction right now. You can see that we have like H beam, C beam that we're going to put it all together. So that's one we call it structural steel. So structural steel, most of the time it has the what we call Young modulus of elasticity about like 200 gigapascal, but it depends on on what they put inside the steel when they are manufactured. And next one is going to be the reinforcement steel. So have you learned lab number, I think lab number 4, the tensile? It's not the tensile steel, right? Not yet, right? The reinforcement tensile. We have cast iron in tensile. We have aluminum in tensile. Not yet, right? Okay. So maybe later. Okay, so if you focus on the steel, can you tell me how many parameters that we're going to use for the steel that Ajahn Siddhichai always mention? We have for the steel, according to the TAS, we would like to test for what? Young modulus, yield stress, ultimate stress, and the percentage elongation. So it's going to be in your examination because Ajahn Siddhichai always put this in the examination. So I also repeat this. Okay. I may ask if you can pick just only like 2 parameter out of this, or maybe I give you like 5 choices and then asking you which one is going to be the parameters they're going to use for the tensile to determine the tensile strength of the steel. So you can just pick sigma y or sigma u in the option. Okay. Look at our first objective. Have you ever heard about stress strain curve as stress strain diagram? I have here. Here, if it is a steel, it's going to look like this. So what can this curve give us parameters? Can you remember? What can calculate from this curve, the stress strain curve? We can find sigma u, sigma y, Young modulus, the slope at linear elastic over here. And lastly is going to be the percentage elongation by calculated with the deformation over L0. So you can just calculate it, multiply by 100. Linear zone, okay? At a linear zone, we're going to apply the Hooke's law. So Hooke's law is basically to tell you that the material can be absorbed energy, and then if we release the load, the material can come back to the same length. Okay, for example, if you pull the what we call the rubber, if you pull the rubber has a really high linear elastic. So next, if we talk about the elastic zone, which allow it to deform a lot. So if you pull it and then you release it, it's going to come back at the same time, at the same length. And next one is going to be what we call, if we call Hooke's law in short. So we allow material to deform, to have a small deformation, which means we're going to use the material in only linear elastic zone, okay, or linear elastic region. But for our field, our material that we're going to use not just only in the elastic zone. Sometimes it can reach plastic. I don't know if you remember it or not. In mechanics of material in chapter 3, we're going to talk about the deformation in plastic and elastic. So what is the difference between plastic and elastic? Can you tell in short? So in short, it's really easy, right? So for elastic zone, if you pull it, release it back, it's going to come back at the same shape. But for the plastic, if you pull it, it's going to recover some length, and then it remain some permanent length on itself. Okay. So in our civil engineer, so we're going to experience two of these most of the time, or maybe in the future you're going to study in postgrad, so you're going to see some ultimate design later. But for our field at bachelor's level, so we're going to talk just only two zones, which are elastic and plastic. So if we look at the curve again, if we go like this, and then we have stress here, strain here, and then we have like this, okay? And what if this is the elastic zone, go up over here, and then we consider this as the elastic zone. But if you pull the stress until somewhere here, which means it's goes to plastic zone. When it goes to plastic zone and you release the load, there will be some recover at the same slope as the linear over here. Okay, it's supposed to be at the same slope, and then the zone we call it strain recover. And then the remaining strain over here, we call it strain permanent. Hope this remind you something from mechanics of material. Have you ever seen this before? Yeah, in mechanics of material. But no worry, we're going to talk about this in the example later, and then also we're going to have a practice for calculate this type of problem. Next, we're going to talk about something we call creep, relaxation, and fatigue. So creep is the failure mechanism of the concrete, which is going to change its shape in a long period. For example, if you put some load on concrete, for example, like for 2 months, 3 months, 4 months, and it shortage, we call it as the creep deformation. And then the relaxation most of the time it's in precast concrete. So you're going to learn it again in free elective course in your 4th year. So the relaxation most of the time occurs with the cable in post-tension slab or precast slab. So when we pull the steel, okay, and if we hold the steel tightly, at some point the steel itself is going to release some force, and it called relaxation. Okay, and next, it may be not, you may not be familiar with this. We call it fatigue. Fatigue. So if you drive on a road like this, for example, when we test for the fatigue, normally we're going to test for the flexural strength first, which you may have heard about this, My/I. Okay, so the fatigue is, for example, if we would like to know, for example, if I get this equal to 100 megapascal of my sample, okay, and this is the concrete that I use to test for the flexural stress, and then I'm going to pick just only 50%, 0.5% of my sigma over here is 50 megapascal, and 0.6, 60 megapascal, and then 0.7 of my stress equal to 70 megapascal. Okay, after I test my flexural stress over here, and then I'm going to apply just only 0.5, 0.6, and 0.7 to the concrete sample, which means I'm going to test the sample like this, this is the concrete sample, and then this one is the support, and then I'm going to test it like this, and this is the P, and then I simulate the load from the vehicle over here, P, and then there will be the dynamic road. So when the vehicle pass on the surface, which means it move like this, and then this one is going to be loading and unloading. Okay, which means when it step on our concrete surface, it's going to load, and if the vehicle pass, it's unloading, which means when I test it, I test at 0.5, which means I allow P over here to have just only 0.5 stress, and then I put the force here and release. I put the force here and I release. After that, I'm going to count for the cycle. Okay. So when we test the static test, we're going to apply force P until it fails. Am I right? So we're going to apply force until it breaks apart. But for the fatigue is, we would like to know the cycle, the life cycle of our concrete. Sometimes it may not fail at 100%. Sometimes if we apply just only 0.5 of the stress itself, sometimes it's going to fail at about just only like 1000 cycle, which means if when we design the road, we're going to give them the what we call service life. For example, this road can be last long for 30 years. That 30 years come from the fatigue test over here. Okay, it depends on the project. For example, if some project they build at a rural area, and then they're going to have the development project later, so they just like design the pavement to have the lifespan just only 10 years, and then 10 years later they're going to come back, and then they're going to develop that pavement again. So this is how we test the fatigue. Okay, next we're going to talk about the stress strain theory. If we look at here, you can see that we have a beam over here. If I would like to remove this out, this is too complicated. Remove this one. Okay, and then for example, if I put something we call dead load, do you know what is dead load? Over here, dead load equal to, let's say this one is 10 kilonewton and this one is 1 kilonewton meters. Okay, and let's say we going to give the span over here equal to let's say 1 meters, 1 meters, and 1 meters over here. And then we have force over here, 10 kilonewton. We're going to rewind back to engineering statics, equal to 1 kilonewton. So if I give you a figure like this, can you find the reaction for me? We can, right? So for the reaction, we can just like take a moment at pin support over here at point A. For example, if I would like to solve this, and I'm going to take a moment counterclockwise, summation of moment at point A equal to 0. I count positive clockwise. So what we get is we're going to get 10. We're going to get 10 multiplied with, we have over here is 1 meters, 1 meters, 1 meters, and then we're going to multiply this by 3 meters, and then we multiply this by 3, and then we're going to get 3 kilonewton at the middle, which means if I would like to find the reaction of By over here, I'm going to get 10 multiplied with 1 meters plus 3 multiplied with 1.5 equal to 3 By. So what is By? Can you calculate for me? I don't have calculators with me. What is By? It's 4.8 kilonewton, right? So if I would like to find the reaction Ay, can I find it? I can also find it by positive going up, Fy equal to 0. We have Ay equal to 10 plus 3 minus 4.8. What is it equal? Going to be 9 something, 8 something, 8.2. Okay. All right. And then for engineering statics, what we can do is draw the free body diagram, and then we going to solve for the reaction, right? Reaction. And then most of the time we would like to know the resultant force at the reaction, and then draw the shear and bending moment diagram only. And for engineering statics, some chapters we also find the internal force. For example, if I would like to find the internal force, we're going to follow the left, I just call it left figure rule, which means when I cut the section, I'm going to follow just only the left image here, left figures here, which means if I cut the section C over here, if you have F equal to 10 kilonewton, and then this one, I'm going to have it equal to 1 kilonewton meters, and then if I multiply the force, so point C is going to be at the middle, so the force at the middle over here is going to be 1 multiplied by 1.5, so it's going to be 1.5 kilonewton over here. And then we have Ay equal to 8.2 kilonewton. Can we find MC, NC, and VC? Can we find here? We can find, right? So what is NC? The easiest one. 0, right? And then what is VC? VC is going to be 10. It's going to be 8. Be 8.2 minus 1.5 minus 10. So it's going to be something negative. Then what is MC? Which means our shear over here, internal shear over here, is going to be in another direction. Can you have me calculate this? 8.5, 10, 11.5 minus 8. So it's going to be 3. So it's going to be minus 3.3 kilonewton. And then we can calculate MC later. Okay, so this is what we did in engineering statics. And if we move on to mechanics of material, okay, if we move on, you guys may have seen this. I think in chapter 6 we talked something about the internal stress and internal shear stress over here, which we call tau over here. So from engineering statics we talk about external load, but in mechanics of material, which is the second class after mechanics of material, after engineering statics, we're going to talk thing about internal stress. So for the internal stress, it's basically computed by internal force N, the one that we just cut the section, divided by A. So it's simple for this, okay? And if I would like to find the internal shear over here, it also can be easily determined by using VQ over IT. Do you still remember this? VQ over IT. Haha, maybe not. Maybe yes. Okay. And then if your beam subject to the bending, so we're going to calculate the internal stress equal to, so this one is going to be the for the bowl for point load test. And if normally if we calculate for the beam, we're going to use this equation, the bending stress, which is equal to my over I. And then if I would like to find the deformation, I also can find it equal to PL over AE easily. Okay, so for mechanics of material, we're going to talk a lot about the deformation of the beam most of the time, and then its internal force. If you remember, this one is going to be VQ over IT, and also if the section is rectangular, you can easily determine the internal shear stress equal to 3 over 2 or 1.5 V over 8. Okay, so just rewind back. And lastly, it's going to be the unit that we use. Okay, right now in Thailand, we are using the metric unit, which most of the time it's in ton per cubic meters. For normal stress, I think normal stress is really easy, right? So normal stress is just the direct loading like this. Stress is the force. We have two force, right? One can be compression and this one can be tension. So to get the normal stress, it's going to be force F over A, or sometimes people just write P over A. It depends on them. Okay, so it can be subject to two force, maybe tension or compression. Next, it's the theoretical proof. So if you have like a bar like this, and then if they cut just only a small piece inside at the middle, and if we zoom in, and then we can determine the stress by using P over A. Okay, so it's for the actual loaded tensile members. All right, and then next one is the shear stress. Okay, the shear stress over here, we're going to talk about something over here, the connection of the bowl over here. So for example, if you would like to determine the shear stress of the bowl, you can just use the V over here divided by A, because when you try to rotate this one, you can see that the bowl at the middle is going to experience the force over here by the grip over here, okay, by the hand grip over here, hand grip. So going to experience this, and then for the shear stress, for this one we call it direct shear stress. It has just only two conditions. One is single shear, and another one is double shear. Okay, double shear just divide by 2. That's it. Okay, if you try to squeeze this down, there will be some force applied to this bowl at the middle. Okay, and then there will be some internal force occurs over here. Okay, at the middle of the bowl. So this is the shear stress. If you divide by its area at the middle area, so you're going to get shear stress. All right, so come to important equation over here. How many equation that you are that you still remember from here? Are you familiar with this? Right. So for the actual force, okay, is the force that directly apply to your sample. It may be compression or tension. And then you can see that the stress is going to be equal to P over A. And then if I would like to find the strain, it's going to be the deformation over here. Deformation. Which means if I pull or push, there will be some, our sample is going to produce some length change over here. Deformation divided by the L0 over here. And then if we apply Hooke's law, you can see that at linear elastic, we can just use this equation directly, which is stress equal to E strain. Okay, and if I know that stress equal to E strain at linear zone, so I can just substitute the stress over here equal to P over A, and then I remain E, and then the strain I know is the deformation over L0. If I would like to find the deformation by in linear zone, I can just find it directly by moving the equation, moving L to the top and then E to the bottom. I'm going to get this equation. Okay. Next is going to be the direct shear. So direct shear mostly on plate and bowl. Okay. For example, if you have the bowl like this, okay, and then you would like to connect the steel plate over here, two steel plate together like this. Okay, so this one we call it the direct shear. If you pull the force over here like this, to the left, to the right, and then we call it direct shear. So you can just measure V and then just calculate the direct shear from the bolt itself. Okay, next one is going to be the hard one. I think we all face the difficulty by this one. We call it torsion test. Okay, do you still remember this equation? So basically, if you remember from the chapter 6 or chapter 7 in mechanics of material, we replace this by using C. Okay, so shear stress of the torsion, when we would like to find it, we normally know the torsion force over here, and then we know the C over here is the radius, okay, of the bar, and then J is the polar moment of inertia. Okay, normally the section of the torsion is circle like this. Okay, and then if we know the diameters over here, and then we can just find polar moment of inertia easily by pi over 2 r power 4 or equal to pi over 32 d over 4. Okay, this is polar moment of inertia of. If you look at this equation, this looks familiar as this equation. Stress equal to E strain over here. Okay, which means for the torsion, we also have the term called G over here is the shear modulus. Shear modulus of elasticity. It's just like right as the MOE. Shear modulus of elasticity. And then our gamma over here is the shear strain. What is the unit of the shear strain? Boom. It's in radian, right? So when we measure it, you need to, if you measure it in angle, so please convert it into radian. And then we also have over here as the shear stress. So basically it's similar to the actual force, but this one we just change it to shear stress by the shear strain over here, and then when we test it, we're going to get the curve like this, and then we can also just find G over here by change in shear stress over shear strain over here. So we can also find the shear modulus. Okay, and if you remember, have you ever you did this test last time, right, in the lab, right? So if we wrap up quickly, so you're going to have a sample like this, and then we have the fixed support like this, and then we measure the length over here, right? We measure L. Okay, and then what else did you do last time? You get the sample, you measure L, and then diameters. Okay, you measure the diameters, boop, 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 over here, and next you're going to apply the torque over here. Okay, right. After you apply the torque, what are the equation that you're going to calculate? Still remember? When you apply the torque, for example, if I start off with this length, and then after I rotate it up like this, it's going to create some angle over here. Do you remember? Okay, so that's your homework. Just go back to recheck it again. Okay, because it's really basic, you need to also remember this. So these are really basic equation that you need to remember, because we're going to use this a lot, whether if you are in third year, fourth year for your capstone project, you still use this kind of knowledge. So please stick it with yourself. And next is going to be the bending moment. So the bending moment over here going to cause the bending stress, which is, if you remember from mechanics of material, it's going to be something look like here, and then we have like the compression strength, and then we have tensile at the surface over here, stress, compression, and then this one is stress in tensile over here. Okay, and then lastly is going to be the transverse shear. So transverse shear basically is the shear that is perpendicular to the surface over here. So this one, and then at this point is going to be the maximum transverse shear. Okay, so you can just go back to last term chapters and then recheck it again. Okay, and then next one is going to be strain. So strain is going to be occurs when you apply stress to it. Okay, you apply stress and then the strain occurs. So the normal strain can be happen in two terms. One is elongation when it's subject to tensile strain, and it's going to cause contraction due to the compression. Okay, so to calculate it, it's really easy. You measure the original length, and then if it's positive, which means it's subject to the tensile strain, because the LF is going to be higher than L0. But if it's subject to the compression strain, it's going to stick with minus, which indicate that your sample is going to be your sample tested under the compression strain, and the unit of it, we don't call it unit less. It has some unit in millimeters per millimeters or meters by meters. It's the same. Okay. Next one is going to be the shear strain. So this one for example, if copy, can I zoom out? Okay, so the shear strain, if your sample, okay, stays still like this, and then it produced this angle at pi/2. But if you try to squeeze it and then it produces some shear stress in your element or in your sample is going to rotate like this. Okay, so at steady state or nothing do with it, it's going to have the angle of pi/2. But when you try to squeeze it, apply some torsion force over here, you can see that it deform. This one deform. And the deformation over here, we give it as the gamma average. Okay, for this one, it's going to rotate just only one dimension because this one is in 2D. So we give it as the AVG, just only one. But for our figure on top over here, it moves two direction. Sometimes it depends on the specimen length. So this one is L1 and this one is L2. So when it's changed, it's going to change at the same time, and then we just like assume that this one is going to rotate. So if this one's y/2 plus y/2, so it's going to be equal to just only the gamma xy's only. Okay, so that's why we're going to have the gamma average over here equal to pi/2, which means the original shape, and then minus the change in angle over here. Okay. And then if you remember it, it's going to be gamma L equal to phi over here by r. Okay, if you like to find the gammas in radian average from the lab, so it's going to be small r over L. L is your sample length from the lab. Then this one is L, and then you can measure the angle over here. You know R, you know L, so you can find the gamma over here. So this the same thing. Okay. The vernier calipers. Okay, or another one, we put some digital gate over here. We call it strain gate. So the strain gate over here, they're going to have like some wire over here connect together. When your sample subject to tensile or compression strain, so the strain gate over here is going to automatically give you the value of the strain. So you don't need to calculate anything. So it calculates for you. Okay. I think if you learn in your postgrad, so you're going to use a lot of strain gate if you test in the lab. So we're not gonna measure it using our hand anymore, because if you measure it by the hand, it's not really that accurate. Okay, so that's why we need to put strain gate instead of the hand. But in our lab, we still use the hand because Achan Siddhichai want you to feel the material, want you to feel and want you to practice it. So that's why we still use the vernier calipers. Okay, so how we measure the strain? We can measure it by two methods. One is the next is going to be the UTM machine over here. This is the digital strain gate, digital vernier. Next, over here. Okay, nothing much. Okay, after we test it, if I put strain gate on my sample, okay, the report that going to provide me, I'm going to get force P over here, elongation over here, and then I input the area inside the computers, and then it's going to provide me the stress and the strain automatically, and then I use that to plot in here. For example, if I test the tensile of steel. Okay. So if you look at this graph, so can you tell me what should we focus on? How many points? Start from the stiff one over here. What are we going to get from here? That first one. What is the first line over here indicate? It's indicate proportional limit, right? So proportional limit, or another word, we call it the theoretical theoretical yielding stress. But for the practical one, we're going to use the one we call it sigma y, or yielding stress. Okay. So from these figures, can you tell me which one is going to be the yielding? We have point A and point B. Which point is going to be the yielding point? Point A, raise your hand if you think it's point A. Point A or point B? Point A, right? Who's A? Raise your hand. What do you think? Which one is point A? Tick tock, tick tock. Point B, raise your hand. No choice, no raise. Not confident enough. Okay. So when we have the graph that can show both uppers and lower yield, normally in our engineering field, we're going to use lower yielding, okay? Because yielding stress is going to be our strength of our material, okay? So to be safe, we're going to use the lower yield, okay? For example, if we compare for the upper yielding stress, you can see that the upper yielding stress provide higher strength, but practically we're going to use the lower one, okay? And then the yielding strain, of course, when it beyond this point, it's going to be beyond the yielding point, which means we're going to, if I would like to find the yielding strain, I cannot find yielding strain from here. It's not the last test point. So it's going to be this point over here. Right. So if we like to find the yielding strain, I also can find from here. Okay. What else? We have first proportional limits. Second one is the yielding, and third one is going to be what? We have 1 here, 2 here, 3 is going to be the modulus of elasticity, which can be calculated by the E equal to change in stress over change in strain in linear zone. Okay. Third one is going to fourth one is going to be the modulus of resilience. Are you familiar with this? Modulus of resilience. Modulus of resilience basically is the energy under the proportional line over here, which is the total area under the proportional curve over here. And it can be easily determined by below's area is going to be 1 over 2 stress multiplied with strain over here in linear zone. Okay, I just write down as PL PL. Okay, so this one is UR. Okay, and then when we run it beyond this point, and then we beyond the yield, next is we're going to the ultimate point. Okay, ultimate stress and ultimate strain. It's the point number 5 that we would like to consider. This point is going to produce slope equal to 0. Okay, so at a slope equal to 0, so this point we can indicate it as the ultimate point. Stress over here. And then at this point, is the sample fail already or not yet? Not yet, right? So if we apply more load, the sample can absorb some more load, okay, until it break apart. At this point, we call it fractures. Or for the brittle material, we call it ruptures. Okay. For concrete, we call it ruptures, and then for the brittle material, we call it ruptures, and then for ductile material, we call it fractures. Right. So we have number 6 is the fractures, stress and strain, and number 7 is going to be the modulus of toughness. Do you know what is modulus of toughness again? Still remember? In short, modulus of toughness is going to be the total energy of material, which means if we would like to find the modulus of toughness, I'm going to delete this first. Just delete it. I'm going to calculate by using this point, which is the strain at failures, and then I'm going to use the yielding point over here at this point, and then if this one is really easy for modulus of resilience, the energy under the proportional line over here, it's really easy. But for the modulus of toughness, we're going to talk about the overall load, which means it's going to be the average between peak and the yielding over here under the curve. So it's going to be area in this side. The TIS 1227 in 1996 over here. Okay, it put like this, still like this, the classification. Okay, so in one table, it's going to provide the chemical composition and also the mechanical properties over here. For example, it's going to write somewhere that they're still going to have the modulus of elasticity at a minimum equal to 200 gigapascal. And then also you need to, before you design your analysis, you need to select the classification. If you remember, it's less than 16 millimeters in thickness or larger 16 millimeter in thickness, you can just check here. And then they provide the tensile strength, which is the yielding. This one is the ultimate point. This one is the yielding point, and this one is percent elongation, and then this one is the temperatures and its energy. Okay, it tells everything. So if you go to the catalog of this SYS company, so the stress strain diagram. So for the stress strain diagram, we're going to, I think you learn this in engineering material. Okay, so it's going to be a similar thing. So for the steel over here, when you pull it at this zone, we call it proportional limit. At this zone, basically we call it the elastic region, which means if you apply load and release the load, it come back to the same point. And when you apply the load and then until it beyond the yielding stress over here, you're still going to deform a lot, which means you're still basically going to rearrange the grain inside, and then it's going to produce a lot deformation at yielding state. After it rearrange its grain inside, you can see that it can resist a lot more load until it reach its ultimate stress. Okay, when it reach its ultimate stress, you can see that the material start to neck like this, and then later it fail at fracture. Okay, at this point we call it strain hardening, and then at the high deformation beyond the elastic zone we call it yielding zone, and then after it has a yielding we call it strain hardening, and then after it reached the ultimate, the necking start to occurs, and then it go to fail. And then we just separate the stage into two main stage. We have elastic behaviors and then we have plastic behaviors. This is how we separate it. Why don't we design steel members beyond, let's say, beyond elastic zone? Can you guess? It's from, yep, that's correct. Because you know, if you tell like your neighbor who's not having any knowledge about civil engineering, so if the beam deform, and then you go and tell them, oh, it's still okay, it's in plastic zone, so they don't understand anything. So for our role, we would like to make the structures to deform as small as possible, or maybe sometimes it's not deform. Okay, that's why if you remember from Ajahn Siddhichai class, he always talk about sigma y is going to be sigma allow, it's going to be sigma y divided by 2. Okay, when we design, we use the sigma allow over here, or maybe not 2, this one is going to be factor of safety, which means our steel is in elastic zone at this point, right, until yielding point. But when we allow you to use not larger than half of it. Okay, which means it's going to produce, if you remember from the start, the Hooke's law, it's the theory to let you have just only a small deformation, okay, to your members. So that's why we're not gonna design the structures to go beyond the elastic zone, okay, because it looks scary, right? One thing to note on this, just only the scale. For example, if you pick one sample and then you test at any labs, but if they give you just only the data for the big one over here, you can just like assume that similar thing, the lower scale over here. Okay, for example, this one is a tensile steel, right? You know that it's going to look like this, but if you would like to get the data for calculating the Young modulus over here, if they give you a big scale over here, can you find it? If I erase it here, can you find the Young modulus from here? So it's really hard, you know, to read the volume from here. But if they give you like the what we call the scale up scale, which means how many times higher than the upper scale, so it's going to be 0.1 divided by 0.001. So it's going to be how many times higher? 10 or 100. So it's going to be 10 times bigger or 100 times. Next is another behavior. This one is a little bit confused, okay, for me also at the first. So you can see that failure of the steel and cast iron subject to the tension load. If we use both material and then you pull it like this, okay, you can see that failure of the steel is due to slipping of a plane of steel grain caused by shear stress. Okay, If we talk about tensile, at the first, we call it actual stress. Am I right? So actual stress is in the actual axis. But for the steel, or we call it ductile material, if I ask you what is if I ask you, or maybe I provide you this image in the examination, and then give you this, and then tell you that this is the steel, and what caused it to deform like this. So it caused by the shear stress because of its failure mode. So it failed at around like 45-degree angle. So this one we call it shear stress. But for the cast iron, so this one failed by the separation of the grain, and then this one I can say that it's failed by the tensile stress in actual over here. Okay, so for steel, the stress that cause it to fail is shear stress, and for the cast iron, the stress that make it fail is the tensile stress over here if it's subjected to the tensile force. Okay, and next is going to be the ductile and brittle. I think you may have heard about it already. So ductile, it's basically the material is going to be deformed before it failures, such as mild steel over here, and then absorb a lot more energy. If it's brittle, it has no or maybe small yielding point, and then it fail. For example, like cast iron or concrete. Okay. Next one is going to be the offset method. This one is going to use in a really premium material. For example, like high strength steel, aluminum, and sometimes it's timber. Because this material cannot provide you the clear yielding point. So what you need to do is you need to do the 0.2% offset, and then you're going to get the yielding point over here, parallel to the proportional line over here. So you can just find it by the offset of 0. If we look at the stress strain curve of the cast iron, you can see that cast iron is really good in compression. You can see that this is, we call it song over here, which means cast iron is really good in compression compared to the tension, but it also can absorb some tension. For example, like the railway base. So if they would like to use the railway support, you would like to use cast iron for the railway support, because of when the train push it brake, so it produce a lot of compression force to the material, which means if you use cast iron, okay, so it's going to provide a lot of compression force. And then if so the cast iron, again, it's has a lot of micro crack inside, so which means if you try to pull the cast iron, so the for example, if this is the surface, right, there will be a lot of micro crack like this. If you try to pull it out, the micro crack is going to be open. When the micro crack is going to be open, the tensile force over here is going to be really small. Okay, but if you compress it like this, the micro crack get close to each other, which means it also provide you some Poisson effect, and then it provide you a really good similar thing. Normally concrete, if we plot over here, so this one is tension and this one is compression, normally we plot it like this, but for this course we have both material in tension and compression. That's why we just switch the axis, so it's similar compression strength, which also increase of the compression area. Okay. And then this curve is going to be similar to what Ajahn Siddhichai taught from last class. So I'm gonna skip this. And then next is going to be our Hooke's law. So our Hooke's law, basically, we talked already that we're going to use the equation of sigma equal to E stress equal to E strain, which means it's supposed to be in linear region only or linear zone over here. And whatever the steel that put the carbon inside, the effect of the carbon is just only the strength itself, but the Young modulus is not going to change. It's going to be having the same Young modulus for the steel. For example, like for the soft steel, low carbon, structural steel, just only 0.2 carbon, it's going to have the same slope, which means the E over here is constant. It's not variable according to the carbon, but it's changed just only in the ultimate. So, but the curve over here is not complete. It's supposed to be something like this. Something like this. All right. Next is going to be the strain hardening point. This one, just to remind you again on the elastic recovery, similar to what we have talked in the first few slides, that when you apply the load over here in the elastic zone and then release, nothing happened, right? But when you try to apply the force beyond the elastic zone, which means it goes up to the plastic region or plastic zone, after you release the force back, unloading over here, you can see that your sample is not gonna go back to the same original point, okay, which produce the length over here. We call it permanent set or permanent strain over here. And then the point that it goes back over here, we call it the recovery. Okay. Which means your sample is going to be, if you pull, and then for example, if you pull your sample until plastic region, release the load back, and then it lost some length, which means it produced the permanent set, and then it also reduced in ductilities and modulus of toughness if you test it again. All right, so this is how it goes. Next one is going to be the strain energy of the unactual stress. It's similar to what I have taught, modulus of resilience, which is 1/2 stress multiplied by strain, which means you're going to be here. Strain PL, and then I'm going to get the stress PL over 2. So it's the area under the curve over here. So here's the definition. Modulus of resilience is the ability that material can absorb energy without permanent deformation, which means under stress PL. Okay. And another one is modulus of toughness, is the ability of material that can absorb energy before it failures. So, or we call it total energy of material. So this is the same equation that I wrote in the last few page. Find easily by using sigma over strain over here. So sigma over here, I can choose any point over here. For example, if I choose at the strain equal to 0.001, because modulus of elasticity, it's in linear zone. So you can just choose wherever point in this line over here. So it's going to be providing you the same number, which means I choose at 0.01, and then it has the stress equal to 220 over here, and then I have the E equal to 200 10 by 3 megapascal or 220 gigapascal. And then question B asks for proportional stress, modulus of resilience, and yielding stress. So this one is going to be the last point before it curve over here. If I plot on here, so the orange point over here is going to be my PL. So I read from curve stress rate and then get 255. Modulus of resilience is going to be again stress at proportional limit multiplied with strain proportional limit, and then I'm going to get this unit for this one. You don't have to convert this one into gigapascal. You can use megapascal, and then you're going to get the MJ over cubic meters over here. And then we have yielding over here. So to find yielding over here, we need to offset 0.2% offset, and then we put it on the line over here by this one. We're going to get 335. Next is the ultimate and fracture. So the ultimate is going to be the highest point 530, and then the fracture is going to be the lowest point below the ultimate. We're going to get it equal to 480. So we get this one. Okay. Next is, what if we pull this steel alloy that's subject to 68 kilonewton? Okay, 68 kilonewton on both sides. So, and then they would like to determine whether the rod is returned to its original length or not. What is the permanent set of the rod? Okay. So basically, some people ask, like Ajahn Siddhichai, why it's always this rod? Okay. So because we simulate from the real engineering problem. For example, if this one is hanging beam, if we provide you this big image, it's really hard to compute for the force over here. Okay, so that's why we just cut the small portion over here and then just rotate it into a rod shape like this, and then put 68 kilonewton for you. Otherwise, it's going to take really long, whether in the examination or in the teaching class. So we cannot cover it within 2 hours. So that's why we just like cut and then give you this problem directly. Okay. But if you like to find it, of course we can. For example, if I have the point load over here equal to 108.8 kilonewton over here, you say that, okay, Ajahn, I would like something more complicated. So I want to challenge myself. So this rod is going to be the two force members. If you remember from engineering statics, we have force P over here equal to 108 kilonewton and then acting to this point. And then if this one is two force member, so we can just indicate it as the force by assuming that the direction is going up, FAC, taking moment at point B to eliminate the unknown. I have FAC over here equal to 68 kilonewton. That's why we provide you equal to 68 kilonewton over here. Okay. And next, they would like to know the elongation of the rod. Okay. So we know that the diameters over here equal to 2, and then the diameters of the small tube over here equal to 15 millimeters. And then we can just find the stress AB and stress BC over here equal to 216.5 and then 384.8. And then if we look at the rod AB, and then the yielding stress is 335. Okay, so this one is less than sigma y. This one is larger than sigma y. Which one is elastic and which one is plastic? sigma y equal to the rod AB is in plastic or elastic? Plastic or elastic? Elastic, right? So it's less than sigma y. So this one is elastic. So when it's elastic, you can just find strain by using Hooke's law. Okay, directly. Which means if I would like to find the strain from AB over here, strain is going to be stress over Young modulus easily. Okay, but for this one, it's in plastic, right? Plastic zone. So for the plastic zone, I need to define this from graph only. And then I use this number. I'm going to plot in here. Okay. For example, it's 384.8, about 385. So it's going to be 385 somewhere here. For example, somewhere here, you can just plot in detail later. 385, and then after I plot it, okay, the big scale is here, 384. I plot it to this point, and then I can find the strain of the rod BC 420.0108. Okay, so I just put it here, but for the rod that's in elastic zone, you can just use Hooke's law directly, equal to this one, a really small deformation. And then we can conclude that this is from graph plastic, and this one from Hooke's law elastic. Okay, and next, if we know that this rod BC is going to be plastic, AB is going to be linear elastic, after we release the load, which one has no deformation? Rod AB or BC? It's going to be AB, right? Which means rod BC is going to have or experience some permanent set, permanent deformation. Okay, but the question is asking what is the total length when it's subject to the force, which means right now we are still pulling, okay, both P, which means if we like to find the deformation, it's going to be strain multiplied with its length over here, strain length. So this one is going to be strain AB, LAB, BC, this one is BC, and then I'm going to get the deformation in total of 4.8. So if I'm not releasing the load, I'm going to get the total length L equal to 500 plus 400 plus 4.8, 904.8 millimeters. Okay. And then the next question, they tell us that when we release the force P over here, both rod AB and BC going to return to original length or not. So this one can be easily tell by this, because we have one linear in linear zone and another one is in plastic zone. So this one is not. So if not, what is the permanent set? So to calculate for the permanent set, we need to consider the rod BC only, because of the rod AB is rod is in elastic zone. Okay, so what are the steps? Okay, we need to, what we need to do is Can I copy this? Okay. To calculate it, at first, we need to find the permanent deformation, right? So we know that rod BC is in plastic zone, thus it cannot return 100% to its original length. Okay. Okay. Which means what we need to do next is one, we need to find the strain recovery. Strain recovery is come from the material itself. So it's supposed to be stress BC. We apply Hooke's law to the rod BC because we would like to find the recovery by its energy. So we use stress BC, which is equal to 384.8 power 6 PA divided by 22010 by 9 PA. We're going to get it equal to 0.00175 millimeters by millimeters. Okay. So this is the recover. And then what we need to do next is we need to find the permanent strain. So the permanent strain is the strain that it can be returned back, which means equal to strain from the curve, strain BC from the curve minus the recovery over here. So it's going to be equal to 0.0108 0.0108 minus 0.00175. So it's going to be 0.0905 millimeters by millimeters. So when we know the permanent strain over here, we can just find change in length of rod BC. So it's going to be L permanent deformation permanent equal to L multiplied with BC multiplied with strain permanent. So it's going to be this number multiplied by 400 millimeters. So it's 3.6 millimeters. Okay. Which means subject to the pull out force, after we release, there will be some force of, there will be some length, 3.6 millimeters going to extend from your sample. If I draw the last figure, it's going to be this one, right? So this one is AB and BC is over here. And after I release the force, the sample is going to have the permanent deformation of 3.6 millimeters over here. If I would like to find the total length, it's going to be LAB plus LEC plus combinant strain. So it's going to be 900. Am I right? 900. Okay. 900 point 903.6 millimeters. So this count we can be